So first talk is about flood aware, which is presented by Nathaniel Hutchison from Wollongong, so very far from here. I'll give you the
floor. Let me mute my YouTube. I can hear you. Yeah.
So you have 10 minutes, I think.
Okay, thank you. 1 second. Okay. Everybody can hear me?
Yeah.
Yep. Okay, sweet. So hi, everyone. As Carol said, I'm Nathaniel Hutchison, and I'm an engineer at the Smart Infrastructure Facility in Wollongong, Australia, just south of Sydney. So in the region, we've had some pretty bad trouble with floods. Over the past 50 years, we've had 33 floods, which you could class as at least serious, and that goes up to extreme. Particularly bad flood we had was in 1998 in August, and that was caused by over 300 mils of rain for a 24-hour period, which caused over 40 million Australian dollars in damage, 100 million today or 60 million euros. And one person died and countless homes were lost as well. Now, to combat that, we now have the Smart Waterways program, a big part of that being flood aware. Now, flood aware combines lots of different aspects of the program together into a near real-time platform, giving everyone an early warning that uses radar reflectance from the Bureau of Meteorology, which comes in every 5 minutes, as well as IoT data from across the catchment, such as water level sensors, culvert status sensors, and other sensors, rainfall, etc. Now that all goes into a model which we've developed in Gamma, which is optimized for speed, and it all is based off some tried and tested models which are used today. Now, the main model we looked at is called the watershed bounded network model, which does what it says. So it takes, if you can see there, that little diagram, it takes the catchment and it splits it up into sub-catchments based off the watershed. You can see that dark black line shows the way the water flows, and the water pools up in sub-catchments and travels down the network to the outlet. That's all defined by a bunch of mathematical equations, which we can see in the code later as we go. Now you can see there, that's the Wollongong catchment. The blue lines show the way the water flows through little streams. The main two streams in the Wollongong catchment being Cabbage Tree Creek and Fairy Creek. We developed a model of the catchment using a DEM and split it up into a number of subcatchments, as you can see there. Now, throughout the catchment, we have, as you can see there, some ultrasonic sensors showing water levels. You can also see Pascal. And we have our cameras looking at culverts to see if they're clogged, if they're going to cause water to pool up instead of flow through. All that data gets sent over LoRaWAN to some gateways and then onto the internet and back to us. So you can see the sensors go over LoRaWAN. The Things network then takes them to Things board, which we have on premises, and Things board puts them in a Postgres database. At the same time, we also have data coming in from BOM, so radar reflectance data, and we can also load it up with data from other providers which we aren't currently getting in real time, but they're good for modeling. Gamma is then connected to the database, and it works quite well for setting up the whole model, and it makes it easy to manage the data. The model works in 3 layers. So up the top, we have a cloud layer, which takes that real-time BOM data. The cloud layer then sends water down into the catchment layer, which pulls the water up, and the water slowly travels down the catchment into the stream, which is like a creek or some other water body flowing through that subcatchment. Excuse me. And then those streams flow all the way down and out to the outlets. As I said before, that's all governed by some equations from WB&M, which we compared our model against. So I'll give a quick demonstration so you can see what I'm talking about instead of just trying to imagine or just believing me. So you can see the catchment there. And as I run it, you can see our clouds dropping water. Now that layer up the top in this particular demonstration is taken from another data source, which takes rain gauges and maps them into Voronoi polygons. So that's how you get those two polygons. I'll now show you the model running with bomb data. So you can see here, it's a little slower, but it's in a grid form. And we get similar results from both, but this data comes in real time. And you can probably hear my computer's whirring a bit more using this data. Okay, let's get back to PowerPoint. So you can see here I've got the code, and basically to get it running quickly, we have to make some optimizations, especially for the radar data. So when we first started, or before I even get to the radar data, when we first started, we also originally had a grid, like cellular automata layer, and that caused a lot of performance issues because it was, thousands to millions of cells, which all had to be run in Gamma. To speed it up, I basically took the geometry of the clouds and overlaid it with the subcatchments. Those subcatchments then used all the geometry tools in Gamma to take a volume of water from the cloud and then take it down into the subcatchment. And then, yeah, all that worked to spread the water across the catchment. So some performance metrics here, we're taking about 7 milliseconds per cycle, which is a 5-minute cycle, using the first model I showed you with the polygons, and then about 55 milliseconds per cycle with the last example with the radar grid. So quite fast and very usable for real time. We just need to improve the initialization speed or get a model which we can launch and then reset while it's still running to improve that side of things. Things we're working on it at the moment and continuing to work on. So we're currently implementing this model in an actual real-time setting. Like it works at the right speed, but we're getting it to the council who will be using it. We're collecting more data to validate our results more. So we have, with the data that we currently have, we've compared a number of particularly bad scenarios, including the 1998 floods, compared those with the existing models that are used by other people with the help of a collaborator. And that works, but we're currently collecting more data so we can look at those comparisons with our own sources of water levels to validate our results even more. We're adding more hydraulic effects. So currently the model is mainly hydrological. So we can take in the results from our culvert sensors, optimizing the model further to run faster. as well as optimizing the parameters in the model, such as the constants and things that affect the flow. And then one last thing that we'd like to add is some further tools to help with theoretical modeling, not just using the real-time data. Yeah, so that's FloodAware. If anyone's got any questions, I know we have questions at the end, and feel free to get in contact with me as well. Thanks, everyone.
Thanks a lot, Nathaniel. And everyone, please feel free to ask your questions on the chat, Slack, etc. And we'll be asking them at the end. We still don't have L1, I think. So the next talk is going to be about escape. Gilles is not, no, Olivier Gilles is not here. So Pierrick will be presenting escape and say a little bit of words about La Soufrière application as well. So the next talk is going to be a bit longer. Pierrick, are you ready?
I think I am. Let's try that. Just to find my...
Pierrick is from the University of Rouen in Normandy. And he's been working on escape for quite a while now.
Can you see my presentation?
Yeah.
Good.
Not full screen.
And yes, the zoom bar prevents me from up. So now, is it full screen?
Oh, it is.
Yep, further works.
Yeah, okay. It's not the right place. I will rather start with the first slide, which is more conventional. Hi everyone, I am Pierrick Lanoise. As Carol said, I am from Litis Lab in University of Rouen. And I will discuss of a project called Escape, which is a 4 or 5 years old project, which involves the IDE laboratory from CNRS, as the project is led by Eric Daudet. UMISCO lab from Vietnam, whose PI is Alexis Drogoul on this project, who brings expertise. So IDE is a lab of geography. UMISCO brings expertise in computer science and modeling. We have a firm, BRLE, which is a firm specialized in advising local governments in the writing of procedures and risk evaluation. And finally, I'm the PI for Litis, a computer science laboratory. I put some author names based on the most recent work described in this presentation, but I could have put a biology paper length of author names of a member of the project, and it wouldn't have been exaggerated. To describe the project, I will first need to discuss disasters and how evacuations can mitigate those catastrophic events. I will describe the project, but to better illustrate it, we will describe 3 case studies and see some aspect of the general escape project through those 3 examples. I will cede the speech to some of my colleagues for some of those examples. Disasters. So the Center for Research of Epidemiological Disasters defines disaster as an event where at least 10 people died or 100 people were affected, or that led governments to declare a state of emergency or to call for international aid. The most deadly natural disaster events are earthquake, and the most frequent are storms and flood. On top of that, disasters can also be artificial, man-made, such as factory exploding or pollution being emitted. Some events can combine both, as happened in Fukushima, for example. Faced with those catastrophic consequences, the population expect their government to try to do something to protect them. When the event is either foreseeable or slow enough, evacuation can be a good solution, as it takes the population out of harm's way. For example, Bay of Bengal in India often sees devastating cyclones. Those cyclones have killed thousands of people at each time until they put in place evacuation. And then the number of people dying shrunk to only tens of people, but at the cost of massive evacuation. Evacuation such as these need to be carefully planned and honed. Otherwise, they could lead to even further catastrophes. If you evacuate too late, you can lose an important part of your population or leave people out in disarray without proper infrastructure to help them. If you try to evacuate everyone at the same time, you can lead to jam, and that puts people in even more vulnerabilities. And
You've muted yourself.
yeah, someone cut my mic. Okay. So everyone hears me again? I don't know why someone, Carol,
Yeah,
or someone cut my mic. Well, anyway.
Your mic. I'm not an admin anyway.
Okay, so
Arthur or Benoit hosts.
okay, okay, probably my mistake. The evacuation itself can lead to injury. To whom those public policies, those processes, exercise is difficult because those are exceptional events. That's the principle of a disaster. So you can't repeat and learn. Hence the idea of using simulation. We built ESCAPE as an agent-based framework to model and simulate massive population following or in a view from foreseeable natural or industrial disasters. ESCAPE aims at helping local governments at writing procedures. So therefore it needs to be quite detailed. We are more of a kids kind of model than a KISS abstract one. To do that, we need to model large territories because complex consequences require to have quite a wide view of the things. So we need a lot of geographical data on population, networks, road networks, rivers, etc. We need to model hazard and their dynamics insofar as needed for the modeling of our events. I mean, modeling hazard can be a full research field in itself. We only do models simple enough to model what affects the population, but we do not go into the fine-grained detail of each hazard. What we delve into more depth is modeling humans and mobility as when the disaster strikes, when it is unannounced, people are leading their ordinary life. So we need to have a starting situation that is realistic enough. Furthermore, when the disaster strikes, when evacuation begins, people get mobile, and we need to see how all the various modes of transportation interact to produce an evacuation result. Finally, we need to model crisis management actors and the way they make decisions and the way they transmit their decisions and instructions to the population. To illustrate this, we will start with the example of Rouen Métropole, which is faced by an industrial hazard that leads to the production of toxic cloud. To present this case, I will invite my colleague Arnaud Saval to take the following of the explanation. We can't hear you, Arnaud. No. Okay, so I will try to do Arnaud's part of the presentation while he fixes his mic. And as soon as he's fixed his mic problem, please help me. So, Rouen is a metropole in Normandy, in northern France. And Rouen is the site of many Seveso sites, which are industrial sites very much at risk, and for which precise public policies have been devised. For example, quite recently, we had a big fire in Labrizol storage in Rouen, that led to the closure of the city for a couple of days, and had important consequences. So we do know that industrial accidents happen in Rouen. So we aim at simulating disasters as a deviation from everyday life, as I explained earlier. So how do we simulate everyday life? We use a generation of households and agenda for those households. We do that by extrapolating data from surveys, French surveys called Enquête Ménage Déplacement, where people are surveyed in quite in depth about where they live, where they work, where they put their children in school, how long it takes them, which ways do they use to do all that, how much time does it take them usually, etc. And then we do traffic simulation that we validate by using, from those extrapolation, we build origin destination matrix. Then we simulate traffic, and we validate this simulation by comparing our result with local traffic agencies. We also use public transport schedules and routes provided by bus companies. The local bus companies is Astus. So we use OSM building data to have residential area, schools, firms, offices, etc., and households that describe 2,600 people or 2,600 households in the simulated area. From that, we must find them accommodation, potential homes for our synthetic population. daily occupation matching OSM places. We make from that an agenda, and we relax some, all this builds a set of constraints that we try to solve, and we relax some of those constraints to reach a solution. Nonetheless, it only builds 2,600 households. We need more. So we need to do some adjustment. Luckily enough, EMD provide a bias that is the way a subcategory is either sub or overrepresented in the surveyed population if compared to the general population. Thanks to that, we can adapt and produce a realistic, at-scale general population.
Pierrick, do you hear me?
Yes, I can hear you, Arnaud.
Sorry.
Joy. Please carry on.
Thank you, Pierrick, for this explanation. So, as Pierrick said, we are trying to generate household agenda and also traffic, and we saw how to generate those household agendas, and we see that for the moment we are only generating 2,600 people. But on the simulation area, we got a lot more people to generate. And how do we do to generate the missing household, missing people, and their corresponding activities? Well, to do this, we are using those correction bias from fine-grained zone we saw just before. Since all the data in the fine-grained zone is statistically correct for the population inside this area, we are generating new people matching those bias. So we know that in a particular ZF, there is some people missing. We are generating those households. And in the same way, we're generating activities. We search place for data from the MD. We are doing the same algorithm to give all our new generated household agendas, accommodation, and daily activities.
Next slide.
Next slide, please. Yeah. So once we generated all people, all agents, we want to make sure that the traffic we are going to generate, that is to say the travel everyone is doing on the day we simulate, is correct and match the distances, match the time, duration given by our dataset. To do this, we're computing an origin destination matrix from ZF to ZF divided by transport mode for every hour. This can give us information to say there is more people using their car in the mornings and in the afternoon more public transport, and we can select the good way for people to move from one point to another, from generated household and agents, to give them the correct transportation mode matching our dataset. That's it for the transport mode. With a little data on bus, since we in the EMD we only have data about the mode of transport. We don't have detail on the specific path they are using to go from one point to another. We develop in Gamma some algorithm to allow agent to select the good bus stop and the good bus line to go from their origin to their destination. Those different paths generated and can have some stopover with several bus lines and so on. And to develop part of the thing, we also develop a new driving skill, allowing people to walk on the roadside or to allow a vehicle or people in the wrong way. So we can have people crossing them in the same roadside, or we can even have vehicle going on the roadside to escape some hazard. You can find some of those developments in the future stable version with Duke developed and presented yesterday. That's it for the simulation. How do we validate our traffic? We run several simulations to compare travels we generated and the agenda and match them with data from local agency, given us how many vehicles we can find on the road during a specific period of hour. And in general, when we run different simulation, we find that we are about 10% deviation in each travel time and number of people, number of vehicles on the road, which seems quite satisfying since we avoid a lot of specifications such as traffic lights, which are not simulated. But it was, well, it's quite enough for us to, it's quite similar to the everyday life to go on and try to start with the main problem, which is how do we escape hazard? Next slide, please. So how do we simulate nitrate gas? Ammonium nitrate gas overall. The first test we made was with Lubrizol event data, even if those data cloud or toxic gas cloud are completely different in type. Well, the reaction and the way people seeing this event was still interesting. There are current projects starting to moderate those other overall, but it's currently starting. Sorry.
We will develop this in the question afterward. I suggest we go faster, Arnaud.
I go faster. So we used all this information about the hazard, and we try to simulate people behavior in time of crisis. How do we do this? We made a local survey about people evacuation, what they know and in the wrong metropolitan area. And we have this repartition of population, which has a third will do nothing when they heard an alert. A third will escape because they know that when there is a gas, since they live in the area, they must confine or escape. And the last third will ask questions, will go to social media to know what to do because they didn't know the official guidelines to how to react in case of a crisis. That's it for the local survey, but for our case study, we need several additional behavior, which are how do the ammonium nitrate gas impact the people and our agents? How do they react when they are in a vehicle, in their vehicle, in public transport? How do they react when they are without vehicle, if they are near the gas or far of the gas? And how do they react with respect to other people who you can see impacting the gas? And all those behavior are coded in Gamma. And that's it for the round case study.
Okay, thank you, Arnaud. And so now we are going to leave the Seine River and join the Loire River in Western France. And Clément will explain us how to simulate flood hazard in the region of Saumur.
Can you hear me?
Is your mic working?
It's working? Okay.
It is. Good news.
Yeah. So I'll present you the flood risk in the city of Saumur in the Val d'Authion. The Val is a wide area of 100 kilometers long, which is quite huge to simulate. But we'll focus the risk management around the city of Saumur, which is a 12,000 people city. And we'll work on the evacuation plan of the city. Okay. On the next slide, you can see what the river look like when it's in a normal way. You can see the city of Saumur and its island. And on the next slide, you can see what it looked like when it's in a centennial flood, 1856 type of flood. So with a peak rise at 6.9 meters. On the top left of the image, you can see that the banks of the river is a straight line because it's a dike. And in our use case, we say, what if this dike has a bridge? So the bridge occurs after the city of Saumur and at around 6 meters. In our use case, we determined that it occurred by night, so that population are at home. So speaking of population, on the next slide, you can see the data we get from the INSEE. It's an agglomerate population in which we can find information like the households with vehicles, the household without vehicles, and the average number of people in each household. The square are 200 meters wide, and we can mitigate this data on the building we gathered from OpenStreetMap. On the next slide, you can see the shape we deduced from the evacuation plan of Saumur. This shape show where the population inside the shape have to go in case of evacuation. So on the next slide, you can see the evacuation point we deduced from the evacuation plan, and which type they are. So in blue, it's the gathering point, so that the bus can take the people to put them, to bring them away in shelters that are safe from the river. And in yellow, you can see the shelters building. On the island, it's the city university. To alert on the next slide, in order to alert the population, we used two types of sirens. The fixed one on the right, which are kind of well known, alerts the population inside the city. And for more well, away countryside buildings, we use mobile sirens that travel through the city and alert the population. This data we gathered from the evacuation plan of Saumur, but we get some too from other city, smaller city around, just like Vivi or Longueuil-Jumelles, which also have mobile sirens to alert the population. On the next slide, you can see a video from the simulation. You can see how wide the area of simulation is, but we'll only see Saumur in order to make it readable. You can see Longueuil-Jumelles et Vivi on the north, and here is Saumur. You can see the building. In red, it means that they don't know they have to flee. In orange, they are currently preparing to flee, and in green, the building is empty. In red, you can see the here the fixed siren, and in green, you can see the mobile sirens that are moving.
Sorry.
It's okay. So you can see the red car moving and fleeing the city. Just after, you can see different different test and view of the simulation. You can see on the top left the rules engine we built in Gamma, and on the bottom right the side driving skill. And here is our latest video, on which you can see in blue the gathering point for the bus. The people, the bigger the points, the more people they have waiting for the bus. You can see the bus coming. Some bus are are in the flood. It's okay.
Yeah.
And the green
The
point.
bar prevents me from accessing the video control. I'm sorry.
Okay, it's okay. It's okay. Well, it's we can. Well, I think that's it. You can see that we put all the information we get from the evacuation plan. So bus fleet, siren, mobile, and everything, and population in order to make the more realistic ABM of the evacuation of Saumur by night during a dike bridge. I think I'll let you present the Guadeloupe case now.
So time is running fast. I will quickly describe a new work we've started this year with Olivier Gillet, who's a new PhD student, on a volcano in Guadeloupe. This is interesting because it adds it illustrates some functionalities that we did not describe for the two previous settings, various hazard, different dynamics, and because for this kind of volcano, we have both ashes in purple that slow down traffic or stop it altogether. We have toxic gas as delimited by the red line. And we have flows, the orange lines, which are not pretty lava flows. They are the dirty gray flows that mix water, ashes, and lava. So very different kind of hazard. So this is interesting to try different things with ESCAPE. We also illustrate some BDI decision making to illustrate emotion and contagion. We investigate spontaneous evacuation, where people decide by themselves to evacuate or not, and influence each other into making this decision. So we have a few preliminary results with a map of the traffic and the speed of the traffic, vulnerability maps, evacuation routes as planned for a bus evacuation, and simulation of spontaneous evacuation of the summit by tourists. So more on this soon, as this work is only starting. So all in all, as through those three examples, you could see that ESCAPE is a framework aimed at modeling massive evacuation and to help local government write procedures and test and evaluate their procedures for those evacuation. To do that, we import and model geographical data to have geographically accurate representation of the towns through census, through maps of road networks, bus and metro networks. We also need a location of shelters, evacuation routes. All this needs to be pretty detailed. We model disasters, floods, pollution clouds, volcanoes in as much detail as needed. We model mobility from very simple to very intuitive, to detailed implementation of surveys and people in our simulation, thanks to the side driving skills that we developed, allows to model pedestrian, bikes, cars, bus, and it's been further developed by the work of Duc that were presented yesterday. Finally, we have disaster management models with static maps, mobile alerts, and road networks management and dynamic modification of the road networks, that is blocking a road, allowing a one-way street to be used in the other way, and these sort of things. In the future, we'll keep, now the framework is quite built. We need to investigate and experiment more with it. We started doing that. So we do what if scenarios. What if we break this bridge? How does it affect evacuation? What if that factory, Lubrizol, that exploded in the night, what if it exploded in rush hour instead? How would it affect the traffic? And we do how-to investigations, how to optimize the time for evacuation, how to optimize the number of people evacuated. Do we need to evacuate everyone at the same time? Do we need a different phase in our evacuation? What is the most efficient? We need to go further, deeper on some of our settings. We're starting work on the Phuoc area in Hanoi in Vietnam. And I've presented a bit of the Soufrière volcano. And then we are working on a serious game that is a simulation for the event to run its way on its own. And we have planned intervention of crisis management. But in a serious game, crisis managers could interact with the simulation in real time, making decisions based on the theoretical procedures and being faced with some contradictions that may not have been apparent. Thank you for your attention, and sorry for having been a bit too long.
Thank you, Pierrick. So the next talk was Erwan, but I cannot see him. So Isabelle or Benoit, who's presenting?
Bonjour, c'est plutôt Benoît, a priori.
Okay. So
Voilà.
Benoit, floor is yours.
You can hear me?
Yep.
Okay, here we go. No, sorry. I need to share my screen first. And okay, perfect. You see me, you hear me, you see my slides.
All good.
Okay. So first of all, sorry to replace Erwan Moal, who was expected to present. So Erwan is a master internship with mainly with Isabelle Ruin from Grenoble and myself, Benoît Godou from Toulouse. And we base the work also on work made by Galaxia 30 from Grenoble. So again, it would be risk management, but more and evacuation. So we build a model about decision and behavior. Sorry, I need to remove. Sorry, I have the face of everybody. It's very nice, but I cannot see everything. So a model, the debrief model about decision and behavior responses for impact estimation in flash flood. In fact, that's quite good that we are after the escape presentation because we are in close thematics. The main difference is that we are focusing on flash flood, so floods that are very fast and quick. And in cases, given this flash flood, where we are not able to have like a huge organization to evacuate people. So we focus mainly on evacuation of people by themselves. So that's why in this model, we will more focus on individual behavior than in the organization to make people escape and to make people evacuate. So to make people evacuate. So in particular, we will have a look at what are the factors that impact the behavior of people in terms of protection or sometimes the reaction facing the flooding. So in which case they can endanger themselves. and how can we try to evaluate the places or the behaviors that could provide more danger to people. The idea in the second step will be to introduce external stimuli like alarm or messages to improve this evacuation. So we build a model with mainly individual people and how they interact with their environment. So the model is based on this conceptual model proposed by Galacia. We will mainly here focus on two parts. So basically that's what we have implemented for the moment. That is people agents, and with people agent, so that means how they react to danger, depending on their profile, socioeconomic profile. And we could introduce also other perception and subjectivity, and how they decide to either continue what they are doing or evacuate or something else. So typically the situation is people on the road, they see that there is water and more water on the road. So will they decide to cross the floods to continue, or to go back home, or to go back somewhere else? And of course, the second kind of agent we'll have in the environment is the other kind of agent we have in this model are the environment, road and buildings, and the hazard, so the flash flood. The case study is Draguignan city in the south of France. It's let's say small city, medium city, let's say, with 36,000 inhabitants in 2010. So here we can see the data we use. So we use available data, basically. So IGN, so French National Agency of Geography, and OpenStreetMap data for buildings, roads. Data from INSEE, so the French National Institute of Statistics, for individual characteristics. And we have data from other members of the project in which this model is built. So I forget to name it, but it's a PIX project. We get some data about the floods. For the moment, we only have a static map of the flood. No. As input, we only have a static map. So that means at the highest time of the flash flood, its extension. So as in the picture. So to build the model, we have a need to introduce dynamics. So to make the flooding evolve. So the level of water increase during the simulation in order to integrate in the dynamic of the model. Okay. So we start by a very basic version of the model. That will be, we have this environment with people located in buildings, and where they have their daily activity that is limited to the simplest agenda, work, home, work, home. And the response to the flood, that is a two-stage answer. If they can see a sign of danger, so flooding, they will return home. If there is only sign of danger, so I mean if they evaluate the danger as limited. But if they look at it seems much more dangerous, they will look at a shelter in the environment. So that could be, in our case, mainly a building with more than one level. So two-level building. In particular, if they are at work and there is several levels, they will go upstairs. The second step will be to introduce heterogeneity in the behavior. Mainly, so we will also introduce improve the routine and add interaction with the agent. But here we'll focus on heterogeneity of behavior. So this behavior I will show it in the next slide. They depend on the individual, and in particular on their characteristics, like male, female, professional status, age, and so on. So we need to generate a synthetic population. So as in many projects using Gamma, we use the GenStar library and only INSEE data to generate sex and age for the moment. The model of individual profile is the following one. Basically, what we want is adaptation behavior. And this adaptation behavior can depend on several profiles of individual and also on what they are doing before the crisis. So in particular, so on the left part, their role before the crisis. Are they like a mobile individual? They go to work or to study. Are they less mobile, like house, husband or wife, retired, and so on? Or is it just like tourists? So basically people who didn't know the environment. We will add to that a second profile that will be a kind of profile in the crisis, or they can reveal in the crisis. So that they could be cautious, skeptical, prioritized obligation, overconfident, or unsuspicious. So let's say overconfident would be basically people who could refuse evacuation, or people who are driving on the road, they see there is a flooding, but they are overconfident and they consider, okay, they can go through. They have a big car and they can go through. And we can observe that this, most of the time, this kind of profile could be really in danger. This profile comes from survey or interview made in previous work, and our objective are to introduce this profile in the individuals and to adapt their behavior. So we are still on ongoing work. So for the moment, we only have age and gender in the individual. Profession and family status will be introduced soon. Okay, sorry, I have a sentence in French. And we have introduced, given this profile, the level of reaction given a signal and alarm. In red would be the next step, like how they react, basically their behavior when they are facing a danger. So unfortunately, I will not be able to show you the simulation because Erwan has the simulation. So I only have the slides, very sorry for that. It's still an ongoing work, but experiment we are doing will take into account, of course, the flood, if it's a fast flash flood or a slower flash flood. And also the message we can provide, various policy, how they impact people. But, and as an output, what we will have, what we want to have is really to focus on individual and what are the distribution of people, what are the distribution, I mean, in terms of characteristic of the population, but so also in terms of space. So what are the distribution of people that are at risk, and also have a map of the places where it could be at risk. So sorry for this little bit incomplete work. That's still an ongoing work. Erwan will finish his master soon, but he will be hired to continue on the project. The PICS project is continuing. So I'm pretty sure that next year, if there is another GamaDays, we'll be able to provide this kind of map. So what is interesting in this work and very good complement to ESCAPE is that here we really focus on individual behavior, on profile of the behavior to introduce this heterogeneity of reaction. So I thank you very much for your attention. and we can answer question during the Q&A session.
Thanks, Benoit, for filling in at the last minute. And our last speaker is Ray Rodriguez, who is going to present about typhoons. Ray, are you here? I can see you. Yeah. Your mic is muted, though.
Hi, good afternoon.
Yeah, good.
Yeah,
morning.
okay.
So the
Okay, so okay, good afternoon, everyone. So I'm going to present our work, spatial agent-based model for preemptive evacuation decisions during typhoon. By the way, I am from Philippines. Okay, for the introduction, by the way, the disaster is already thoroughly discussed by Eric during the escape presentation. So what I can add is that Philippines is a disaster-prone country, actually typhoon-prone, because Philippines experiences at least an average of 20 typhoons per year. Okay, at least those typhoons who enters Philippine areas of responsibility. Now, this is because of our proximity to the Pacific Ocean. And then it's also important to understand how humans behave and make decisions during disasters, which could help in response and rescue efforts. That's why we decided to model preemptive evacuation during typhoon. Okay. So our objective for this study is to initially understand how perceived risk influences the decision of households to preemptively evacuate during typhoon using agent-based modeling. So we have the 3 decision factors. We have the decision maker attributes, the capacity-related factors, and then the hazard-related factors. So these factors are those factors that influences the household decision to evacuate. The location of the study area is at the southernmost part of the Philippines. We have here the Sorsogon province, and then in the Sorsogon province, we have the San Vicente village. From that, we mapped the village using OpenStreetMap, and then edited it, downloaded the OSM file, edited it using QGIS, and then we imported the shape files to Gamma. Okay. For the model, we have 3 types of agents. We have the household, rescuer, and shelter manager. For the household agents, these are heterogeneous agents. In this model, we have 570 agents, and then the attributes are based from national and local household and housing census. But in this stage of the model, rescuer agents and shelter manager agents are still homogeneous. We have 15 agents for rescuer as well as 4 agents for shelter manager agents. Okay. There's also perception distance for the 3 human agents. When we say perception distance, for example, in the rescuer, it has a 50 meters perception distance. So if a household agent is within its perception distance, we can say that the rescuer has seen that agent. Okay. We also take into consideration the public storm warning signal in the Philippines. We have storm warning signal number 1 up to 5. And then we have also the rainfall classification or rainfall severity. We have the red, orange, and then the yellow. We're in the red color prompts evacuation. In this model, we only considered typhoon signal number 1 and 2 because that is for preemptive evacuation. Preemptive evacuation happens 24 hours before landfall of the typhoon. Okay. For the characteristics of decision maker, we have the following attributes. We have the head of the household, house ownership, a level of education, presence of young children, the presence of household member with disability, the income level, presence of elderly, and length of stay in the residence. For the hazard-related factors, or HRF, we have the storm severity, the rainfall severity, and the proximity to the source of the hazard of the household, the source of evacuation warning, which could be friends, media, and authorities, and we have also the time of day. We gave values for those variables, ranging from 0.25 up to 1.0. Then we have also the capacity-related factors, or the CRF. The variables are house quality, house floor levels, and past typhoon experience. And then with those variables, we compute for the CDM, HRM, and CRF values by adding the values of those variables. And then after that, we compute for the perceived risk for each household agent. So to compute the perceived risk, we have the CDM multiplied by the weight of the CDM plus the HRF, and then the assigned weight, and then plus the CRF, and then the assigned weight of the CRF plus bounded rationality. This weight is like assigning importance to a decision factor. So the value for the weight for CDM, HRF, and CRF starts from 0.1 to 0.8. Okay. The highest possible score for the perceived risk is 8 times, of course, the weight of the CDM plus 3 times the weight of the CRF plus 5 multiplied by the weight of the HRF. The 8 refers to the number of variables in the CDM, 3 also for the variables of the CRF, and 5 for the capacity-related factor. Now, for the household agent to evacuate, it will first execute this. If the perceived risk is greater than the highest possible score multiplied by the threshold, then the household agent will evacuate. Otherwise, it will stay in its house. Okay. So this threshold variable is the assumed perceived limit of what a decision maker can hold before deciding that the best action to do is to evacuate. So in our simulation, we have the values. The minimum value is 0.7, and then the maximum is 0.9, and then a step is 0.1. We have also here the input parameters for the model. Okay, for our experiment design, we use the exhaustive exploration method. Okay, with 7 input parameters and only 1 outcome parameter, which measures the number of households who evacuated. Okay, so if the total weight assigned to decision factor is less than 1.0, then the current possibility simulation is skipped and proceed to the next one. Okay, for our model visualization, we have here at the left is it shows household agents evacuating inside the village. We have here four buildings which are designated evacuation centers, colored blue. So if it is not yet on full capacity, it is colored blue. But if it reaches its capacity, then it will become color red. On the right graph image, household agents are evacuating outside the village. Okay, so at the start of the simulation, parameters will be initialized, and then the rescuers will be deployed to inform households about the incoming typhoon, okay, and also to conduct preemptive evacuation. And then household agents will compute their perceived risk. Okay, so upon knowing their perceived risk, they will have to decide whether to evacuate or not. Okay, for the result, we have here the batch experiment result. We tried to graph each possibilities. For the 70% threshold, we have the following. We can see that the number of household evacuating is still too high. So the number of agents are 570. So the number of household evacuating are almost reaching the number of 570. Using the 80% threshold, okay, the numbers of household evacuating decreases. And then for 90% threshold, the number of household evacuating really decreases. And then if we compare the result to real world data, we have here, okay, in 2009 typhoon, one of the typhoons during 2019, there are 66 households who preemptively evacuated, and that is nearly match this situation. We have here graph C, signal number 2, orange rainfall classification, and during nighttime. So in the real world data, we have 66 households who preemptively evacuated. In the simulation, we have at least 45 to 37 households who evacuated. Okay. So for the conclusion, the Gamma model showed that among the perceived risk decision factors, capacity-related factors contribute significantly in the decision of household agents to evacuate. And then the characteristics of decision maker in household and hazard-related factors also contributes, but not as significant as capacity-related factors. Another deciding element observed is the threshold of evacuation decision. Thank you very much. That is the end of my. By the way, our ongoing work that is applying the model on investigating under what conditions will cooperation emerge between affected people during typhoon evacuation. Thank you.
Thank you, Ray. Thank you to all the presenters. We're going to the question and answer session. So I've been noted quite a few questions from the chat. Maybe some have been partially answered, but the first question was for Nathaniel about the users. Your simulation was quite impressive with all the sensors, this unusually use of gamma. So who's using that at the moment? Are the councils using it already? How are they reacting? That was from Nicolas. Is the visualization sufficient? That was from Patrick.
Yeah, so currently we're deploying it for a real-time use with the council, so the local council. And they're happy with it so far. It's just getting it from our system to theirs. And then once that's working, well, basically I've got everything ready for them. I'm waiting for feedback from them on how it works. Once that's up and running, what we're doing next, which I talked briefly with a few of you about on Slack, is I'm developing a web platform to take the headless system, the data from it, and visualize it, give fancy graphs, the catchment, where water is, whatever they want. That's the next stage. Also, there's another, there'll be other stages for putting more model functionality in, but in terms of council, it's the interactivity and visualization abilities that they're concerned about.
Cool, thanks a lot. Another bunch of questions were regarding surveys. So Nathaniel was asking for the escape model, which sort of questions were asked in the survey. And then Sri Rama was asking, how do you trust the answers? And Frank also, because the behavior that are declared in a survey are quite different from the real behaviors then. So maybe someone from the escape team.
Yes, I will take this one. So, knowing how people behave under duress and during a time of crisis is not something very well known. So, how do we do something starting from this point? We used military experience because although it is different, it is people who are under danger, under the threat of death, and experimenting fear and trying to still attain goals nonetheless. So we used, and furthermore, the military people have the good idea of liking minutes and debriefings of how things went, what went right, what went wrong. So we used books like Sous le Feu, that help us to build some of the profiles of the kind of reaction we can have. But the reaction has also a part of knowledge, of risk culture. So in the surveys, we try to assess whether people know what they're supposed to do. Do they recognize sirens? The answer is generally no. Do they know what they're supposed to do depending on the sirens? Generally no. And they like to keep in cars, which may not be the right answer. They're supposed to reach in France buildings called établissements d'accueil du public. And but those kind of buildings sometimes do not know that they're supposed to welcome people trying to find shelter. So knowing what is known and unknown contributes to our building of the response. We do know that the response under stress will be different from the theoretical response, but those theoretical responses do bring knowledge, like, for example, on where the knowledge lack. People will not invent the correct procedure if they do not know it when everything is going well. It's links to another question that was asked on Benoit, on the way you have different profiles for your agents. Some are cautious, some are overconfident, and so on. And the problem we face is, how do we know which part of the population will fit each profile? Finding the existence of the profile can be done. You can find it in minutes, you can find it in work. So we do know that there are several tens of people that will behave on the different profiles, or what we call the different tactical alternative. But which part of the population will behave in this way is quite difficult. So Isabelle explained in the chat that she may have some ideas on the question. I'm very curious on that.
Yeah, then maybe Isabelle or Benoit can tell us a bit more about how to link the profiles with those, from those surveys, and to find out which categories of people, like tourists or elderly, isolated people, fit in which profiles then.
Well, hi, I'm Isabelle. So basically, what I've done in the past, so which is not yet implemented in this model, is that we made big surveys about, so two types of surveys basically. One is more a quantitative one based on questionnaire, where you ask what they would do in such situation. So of course, it's not what they really do. But it's a first guess, let's say, and at least it's the best they can think of. And the second type of survey is more related to what they have done in past events. So basically, we made some interviews after flooding, a few months after, and to kind of reconstruct all their activities during the time of the flooding. So basically, they would tell us, every 15 minutes or so what they have been doing and why. And so basically, it helps to make links between their action, protection or not protection, actually, and the information that they get from the warning, the official warnings, or from their families, or from other type of information, their perception of the environment, and also we can relate it to the feelings that they had, like emotions, something like that. So that was very rich information, only for few people that, some tens of people that we interviewed, but of course it's not giving us like strong statistics. So but we made some links between those qualitative results and also the quantitative results of the interview and the questionnaire surveys. And somehow we can link the proportion of, so let's say we make ascending hierarchical classification based on the questionnaire survey that gave us some kind of 6 different types of behaviors during crisis. Of course, they would say they would do, and those could be related to some profile, which are related to the age, the gender, the familial status, because it would be also related to the idea of going to pick up their children, or and also their schedules, because all this is also related to their motivation to do something during at that moment. And the motivation, it's kind of competing between carrying their routine, which is an important motivation, and protecting themselves. And all this is balanced by their perception of the environment, or all the warning that they receive from both official and non-official sources. So that's what we are going to try to put in this model, is to somehow use these profiles that relate those type of variable, social variable to these basic, let's say, behavior aspects. Of course, for tourists, we had also for tourists we also have this questionnaire survey, so we can also try to put this behavior, even though of course the distribution of tourists in the city or will not come from INSEE data, so we'll probably have to use something more let's say sorry, I can't find the word, but we'll distribute them in turistical centers, something like that. So yeah.
Okay. Thanks,
Yeah.
Isabel.
I would also complete by saying that it depends also on the hazard itself and the speed of the hazard. It's not necessarily Hollywood-style panic with people screaming in the streets and meteor falling from the sky, or being trapped in a building and in fire with the fire 1 meter away from you. The disaster
Well,
can
that
last
we
the
had.
whole day, and so you can have the time to make decisions. And so what you declare in survey will be closer to what you do in a kind of disaster where you have 1 day to react, for example.
Even though you have 1 day to react, it's still a different stress than being behind the screen and having to declare something. But regarding the type of disaster, we had a different one with Ray about typhoons, who also has a model with some individual factors and some place-related factors. So maybe a question for Ray. Do you think your model, your different factors would also be important in decisions in other kinds of disasters?
Sorry, it is a question from Ray to me, or
Ray?
Ray?
No, it's to Ray.
To Ray, sorry.
Because we've seen a number of different models who have lots of common points. So.
Yeah, as for now, it is only for typhoon-related disasters. So I'm not yet aware of other studies that uses those decision factors to other disasters.
Right. So we've had a number of discussions actually since yesterday as well about the genericity and reusability of all these. We've seen models for traffic that are used in ESCAPE and in the urban models we had yesterday, etc. We have a question from Frank to Benoit about using the Ben architecture, about fear, contagion and stuff. Benoit, do you want to answer that? Benoit.
I think Benoit has left.
Okay.
He said he had another meeting, so.
Oh, okay.
If the question is whether we used it yet, it's no. We maybe will use it later, but for now our model is still quite young and not very much detailed.
Anyway, it's time for the break. I think we're already 5 minutes late. So thanks everybody, and see you in 5 minutes for the next session.
Thank you.
Bye-bye.
Bye.
Okay, hi everyone. So I will be the moderator of the very first session about participatory modeling and simulation with Gamma. The first session of the three of those, I think. The three next session will be about participatory modeling. And this first one is very exciting because there's three different, very contrasting approach for participatory modeling. And because we are a little bit late, maybe we can step into it directly. I was looking if Etienne Delay was there for the very first presentation, but I don't think it is connected. He is connected, sorry, yet. Etienne, are you here? I don't think so. So maybe Irina, if you're there, we can.
Yes, I'm here.
Okay. Good morning.
You
good
want
afternoon.
to swap the presentations?
Yeah, if it's okay.
It's no
for
problem
you.
for me. No problem
Okay.
at all. Yes.
So we'll go directly into your presentation. So you from Netherlands, and you will present Synerta, which is a business process interactive tool. If I understood it correctly. So you have 20 minutes, and I let you speak.
Okay. Thank you very much. Please confirm that you can see the image coming through.
Yeah, perfectly.
Yeah, good. Good morning, good day, good afternoon, everybody. I know there are people all over the world here. My name is Irina Pushkina. Thanks so much for letting me, giving me this opportunity to speak. And this presentation will give some insight into the interactive tool, which has been developed by Schuberg Phyllis for visualization and simulation of the business process. Let's go further. Just a little bit about Schuberg Phyllis. I will not spend much time here. This is the Dutch company, which has been founded already 18 years back, constantly growing. It specializes in different areas in data and cloud native software, mission critical applications, and outsourcing qualified people for supporting really the customers. For quite some time, we deliver a high H solution. The customers which we cover mostly are on Dutch market, but we also have those who are extending their business abroad. And the area varies really from manufacturing to transport logistics, retail, energy, payments, banking, asset management, and insurance, and the list can continue. So what we learned from the customers is that there is constantly the demand for simplification of the business process, for visualization and predictiveness in the decision making. On the top of that, what is also very important is that the customers would like to be included in the decision making, which is not quite often happens. And normally a solution is developed and delivered as a package with all consequences which we have coming from there. So how can we talk about the business process in general? And talking about the customer, it's logical also to ask, what position do I have in the logical chain? What will actually impact the chain, and how can I myself adapt and change my business model? That will bring some consequences. All these questions arise, and if the customer works on the market for quite some time, it's already difficult to have a quite good overview of the business process due to complexity. So what did we do? We started from the mood boarding, from the question, how can we really approach this process? First, case by case, involving a lot of visualization, thinking about chains and agents and how to put them all together. There were quite interesting people coming our way, those who are specializing actually in Lego world, and building the whole prototypes out of material they have. which gave us some idea to search even further. And we ended up spotting the technique of MIT Media Lab, which developed the Cityscope. And the Cityscope helps in the city planning. And the idea seems to be quite simple. Technology is never simple in general, but it's interactive, it's entertaining, it's really appealing, and it gives really ideas and grasp on the things which people see and touch. So what they did, and probably most of you already know that as well, they develop the view of the city, which they can build with the Lego bricks. And by modifying the position of Lego bricks, which are buildings or streets or any objects around, they can see how population actually develops. They can see how it influences the traffic. And making conclusions out of that, they can advise, for example, on the planning, which is strikingly simple but beautiful idea. We picked it up and we developed the first prototype. The first work has been done completely on the table with a simple paper light and even projector hanging from the ceiling on the ropes. But the first prototype has been ready, and the first working demo of MIT group has been developed and was working successfully. So we had the second prototype. You can see the table here with the projector under the ceiling, which the first object which we had. Something to mention here, the MIT Cityscope is the open source library, which is available freely for downloading, but it's not really functioning fully the way how we want, and we really wanted looking deeper in how everything works. We wanted the full interactiveness between really playing with on the table and seeing how simulation reacts on that, visualizing it on a screen, involving maybe some 3D imaging in order to, and have some predictive analytics on the top of that. So there are a lot of loops which are actually sending data, receiving data, and the package which we had at that moment was really not suited for that. So we worked further, and that's what we ended up with. This is the architecture of a so-called synergy table. And the idea behind synergy is that you can imagine that 1 + 1 is not only 2, but it also can be 3, meaning people get much more from really applying this technique and playing with that, and can be involved in interactiveness and communication. What you can see the table with the interactive agents on it. They're represented by the Lego bricks. Each Lego brick has the marking on the bottom, which is called tags. And all this information is sent to the camera, which uses OpenCV for scanning the location, the combination of the tags. It recognizes the image. And it should be calibrated in order to fit the image on the grids. And sends the information, uses AWS Cloud for storing the information about the grids, which includes the location and the tags. This is now further on communicated to Gamma. We're using the Gamma engine for simulations, which immediately picks up information, and the model which you build will actually, this data will be fed to the model. So it reacts immediately and adapt all the analytics which you produce as an output and shows you graphically whichever way you prefer. And it also communicates with the projector, which needs to have the data in order to project the image on the table. So there is this constant loop of 3 loops between projector, camera, and the table. So how does it look like? We have a simulation, which is a discretized image. You can put any geographical area, piece of geographical area on it, discretize it. For many of you, probably this example is familiar. It's we took it to show from manuals of Gamma, actually. And it's also on the table. And Gamma has a continuous image and shows much more than you can see on the discretized image. So we had the first model, which actually was developed in the energy sector for a customer, which shows the modeling of the solar energy, collecting the solar energy depending on the day of the time, depending on the location. So there's the whole model sitting there, which was made especially for the energy sector customer. This first prototype opened even more questions to us, because what we want to simulate, it's really deeply depends on the research question which we want to focus on, because it's very easy to do too much, but the whole purpose and idea was really simplicity and interactiveness. So we use Gamma for agent-based simulation, and agent-based simulation is the topic here. There should be a very good engine for visualization. We use Unity game engine in order for creation 3D world, which guides actually the customer through the whole business process. And at the same time, by playing on the table, you are interacting with the model which you are simulating. It's also visually quite appealing. You can zoom on particular area which is problematic, for example, and model the process and ask a lot of questions which address what if scenarios. It's appealing because the beamer is also projecting the map and the simulation surface, and at the same time you also can see the 3D world where you can include all kinds of technologies for making it even more advanced. So the next showcase has been transport and logistics showcase. You can see here the whole setup, which explains actually how that works. In the center, there is a table, and the piece of simulation which you see here, this is the map which shows the port. It's roughly the roads with the ships and the location of the with the ports or the warehouses. And it simulates the traffic between the warehouses and the cranes which are supposed to serve the ships, either to load or offload the containers on the ship. And I would like to show you the piece of simulation which demonstrate this technology in action. So in the left bottom corner, you can see the table. There is nothing set up yet. And on the right side, you can see the geographical area, which is just an example how it works. We have the crane, which has a marking on the bottom, is a combination of the tags, and we place it anywhere on the table. You can see that simulation software immediately picked it up. We have the warehouse, which can be either import logic or export logic. This one has import logic, meaning it sends immediately the trucks with the containers towards the ship. And we introduced, it's very easy to use optimization here and ask to use the nearest possible, the shortest nearest path between the warehouse and the ship. There's also export container yard, and we distinguish them by the color. You can see it also on the table, that two types of logic, you can clearly distinguish it. You can go even further with advancing it. But the whole idea here is you can think of what is in your business model. How busy, for example, the traffic is of the ships coming towards the port. Statistics you can feed yourself. You can, by one rotation, this is, by the way, the customs. This is one of the restrictions you can put on the table in this particular model. So this is a smart kind of control. You can, by positioning it on the table and rotating, you can control the percentage of the trucks to be screened, which are bringing the containers, import containers. For example, the ships are coming from abroad. Right now, you can see a small circle, which means this is only 20% roughly of the trucks will be screened. By just sweeping one of the agents, you can change the logic between export and import, and you can inject actually more statistics in your model. So right now we add more trucks moving. You can see the data as well, because the data is wired such that we keep an eye how many containers are right now with each crane. And at the same time, you can ask the question, what is the logical position, for example? Okay, with this kind of setting, does it make sense to place the customs so far at the bottom? Maybe it makes more sense to place it somewhere close by to the port, and increase also the screening ratio. So right now it's the big circle, which is around 80% of the trucks will be passed through the control. Some of them will be identified with dangerous goods or something, and they will be taken out of the business model. Some of them will be checked and approved, and they can continue further. So you can endlessly keep on asking here questions. And the beautiful moment here, it's a simplistic, it's visual, it's interactive, and the customer starts talking about really everyday process, how it functions, coming up with the use cases to look even further. So that's the case. I will stop simulation and show further. So that was the example on the transport and logistics. Recently, we developed another example, which simulates the customer journey. And that simulation is based, it's quite interesting, and at the same time, really involves a lot communication with the customer. And it's based on the behavioral patterns of the humans. What you see here is the setup for the airport. It's very simplistic, but it's agent-based simulation, meaning that you really talk about the agents and their involvement in this chain. What we did, we represent here 4 zones, like check-in zone, passport control, security clearance zones, and at the end, boarding zone. And we let passengers to enter the terminal. We set up the belief for each of the passenger. They have to find the entrance to the queue. We force the passengers to respect the personal space and wait for other passengers, and further proceed towards the passport control. Here you can talk about technology. You can talk about, for example, technology. There is a manual control, which involves people, and there is the automatic control, which let passengers to flow more rapidly through, and there is no actually people involvement in this process, which normally passengers try to avoid. We all prefer to go through just automatic and we're out. So yes, the model is made by the human, and yes, we're given the features which we believe are true, and the model has to be adopted, and there should be true information which you are feeding this model, garbage in, garbage out. But it is quite doable in order to pick up the features of the whole model itself. So let's go a step further. Just to zoom in on this construction. So what is it all about? It's one thing is that highly intuitive. From one point of view, it reminds the serious plane with Lego. From another point of view, it also gives immediately the feedback. There is a response. It's quite interactive, and there are no pre-saved scenarios. So nothing what we are feeding, we are playing on the table, nothing is pre-saved. The simulation itself includes really real-time intervention. You can put on a table geographical area, and yes, the table is small, but that's not the problem. It all depends on the problem which you would like to zoom in. The table can be extended. It can be made even bigger. The resolution can be also improved. But we can use the power of Gamma simulation platform to include a lot of features to catch up the really behavioral patterns or characteristics of the objects. For example, traffic lights, multiple lane roads, speed limits, congestion effects, statistics following something is broken, something not. So there is a real-time feedback loop of all this simulation in order to help customers to evaluate their business process. And the most important, no way this is not a predictive analytics tool. It is really tool which supports the decision making. So there are a lot of what-if scenario with which we can play, and a wide scope of the business problem, which we can zoom in and talk about. So what can we get? What kind of insights can we get? We can get insight in total business process, sub-process. We can see the value streams, information streams, the data flows, and some telematics of the individual engines. About Gamma platform. This is really powerful tool, and it was quite a learning curve for us as well. And there are still some questions which we have a glimpse on, or we would like to have answers. I would like to have answers. So if somebody of you have experience with that, please reach out. Would be interesting to discuss this. So can Gamma integrate with, for example, AWS? And it will be also nice to have a event-driven base simulation support. And in that, I mean more really advanced support for event-driven simulations. Can Gamma react to events outside the Gamma environments? And for example, the web-based environments. Can we have the webhooks? Can Gamma send data? We didn't discover that way yet. So this is one of the stumble stones we have. And just another one to add, I discovered a lot of broken links to documentation and tutorials on the website, which makes it a little bit uneasy to really dive into Gamma, but it would be really great to have some manuals. Manuals right now are great, but those links which are indicating extra information would be really nice to have them all available and up to date. I think I'm pretty much in time. Thank you so much for your attention, and I hope to talk to you outside this panel. Thank you.
Indeed, you perfectly on time. Thank you very much, Rina, for this brilliant presentation. And I think Etienne is not there. Are you? No. So I think we can go for Ahmed presentation. Ahmed Latabi, are you there?
Yes, I am.
Yes,
Can you
perfect.
hear me, please?
Yes, I can hear you.
Thanks.
So you will be talking about LithoSimGen. So here we'll be talking about serious game about flooding risks. So we keep up with the thematic of flood, but with the serious game aspect here. So Ahmed, I let you speak. So you have plenty of time. 10 minutes.
Is it good?
Plenty of time.
Can you see my screen?
Yeah, perfect.
Okay, thank you. So today I will present you the LithoSimGen, which is the generic version of the LithoSim model. And since we are in GamaDays, I will focus more on the technical side of LithoSim instead of social and scientific side. So I will not talk about results and workshops, etc. I will stick to the technical side of the model. So what is LithoSimGen? So LithoSim is a generic, LithoSimGen is a generic version of LithoSim, which is a participatory simulation model. In other words, it's a multi-role serious game of flooding risk management, where a set of decision makers and technical experts are gathered in a room to play a game during about 10 rounds workshop. In these rounds, these players are invited to do a set of land use and coastal protection actions, such as building or removing dikes, urbanizing areas, moving population far from the coast, turning areas from agricultural to natural, etc. So the goal is to teach these people how to deal with the flooding risk. And unlike the other project, LithoSim is is not a real-time response to the flooding risk, but its goal is to teach people how to deal with the flooding risk in the long term. So it gives a long-term response. It means that decision makers have to test scenarios to learn how to better plan for their strategies in the long term. So how to do this? Lithusim is composed of three main roles. The manager, which is played by one of the Lithusim team. He is the animator and the manager of the game. The second role is the leader, which represents an hypothetical risk agency. Its main role is to supervise the game, to push players towards more ecological and alternative strategies to deal with the flooding question. And finally, the player role, which is played by decision makers, by playing teams. It's usually for teams that are playing a Lithusim game, so we cannot deal with more teams for time purposes. So 4 playing teams are dealing with the animator of the game who controls the game, the flooding events, etc. In the leader role, which is the risk agency. So the architecture of Lithusim is like this. We have a powerful machine. It should be under Windows or Macintosh because the LizFlood doesn't have a Linux version. So this machine, there is Gamma, there is ActiveMQ for the networking, and there is the LizFlood, which is a 2-dimensional hydrodynamical model that models the fluid extent. There is a video projector with a screen where the flooding event are projected to the whole people present in the workshop. And the leader role is also on another machine, on a separated machine. And the 4 playing teams have tablets. Well, they can have also personal computers, but tablets are more playful for this kind of games. So the material architecture, the only condition of this material architecture is the Gamma. So whenever Gamma can be installed, whenever we can have Java, so Lithusim can be played even on a phone if we can install Gamma on a phone. And how this is done technically. So Gamma, which we call here the Lithusim Gen platform. So it takes the 2 grids, the digital elevation model grid and the rugosity grid. The rugosity is the resistance to water. So we send these 2 grids to LizFluid FP, which uses some parameter files. The LizFluid calculate the real fluid extent and send back about 14 grids back to Gamma, to Lithusim. So we can show the flooding event gradually, like if it is a real visualization. As we can see, everything turns about Gamma. So I will talk a lot about Gamma and how we implemented the model using this platform. So Gamma makes it easy reading and writing text files. It offers simple primitives with advanced operators to deal with data. It supports different extensions, and we can also read and write agents directly from files. So these features are widely used in Lithusim to read, for example, configuration files. Lithusim uses a lot of configuration files during initialization to read different parameters. And this is this feature that makes Lithusim Gen a generic platform, since we can read parameters of different territorial archetypes. So we have a generic and dynamic model that can also export, of course, export data to files and save results. It's the same with the geospatial data, as Gamma can also read geospatial data with simple primitives. It also gives advanced operators with different extensions. We can also create agents directly from special files. And LithoSim uses also these features to, for example, to create agents, saving their states to textual, but also to shape files. We have also a pre-processing step where we transform geospatial data, brute geospatial data that doesn't have the format requested by LithoSim. We use a set of R scripts to transform this data to the structure that we use in LithoSim. So we have a mapping XML file where we do the mapping between the original data and the LithoSim structure of data, and we can do the automatic transformation of geospatial data. This also helps LithoSim to be a generic and reusable model, which is a question that we raise a lot even during these GamaDays. So the use of geospatial data makes LithoSim a realistic game since it offers a realistic environment to the players that already know their territory, which makes it also a ludic simulation that is attractive to play. Gamma has also the capability of using ergonomic interfaces, which are not really easy to build, but once we do it, they are really easy to use. For example, playing teams in LithoSim use just mouse clicks in tablets to do their actions on the land use areas or on coastal defenses. This makes LithoSim easy to use for a large public. So LithoSim use really huge grids, more than thousands of cells. Gamma makes it also easy to deal with large scale models, especially that we can implement millions of agents, and it can also run parallel processes. In LithoSim, we use this feature to load the digital elevation model, the rugosity grid, and to simulate also gradually the inundation. But during this experience, we can see that once we go up, well, 1,000 cells in height or in width, the LithoSim, the Gamma becomes a little heavy, and it takes time to refresh the screen. It takes time to make some calculations, etc. So one thing, it's a question for Gamma people, is if we can have subgrids. So a grid will not take the whole world, but just a sub area of the whole space. So for the network, LithoSim Gen can be played over the network. It's a remote game since we use Apache ActiveMQ. It's also an external software of Gamma, but we can, within Gamma, we can call any external software. But for the network, it offers simple primitives such as connect, send, and receive to share data to a shared mailbox with topics. And Gamma gives us also the possibility to serialize directly agents and to send them to the network. So inside LithoSim, inside each role, in each model, we have some network agents that send and receive data from others. So ActiveMQ, but also ListFluid FP are external softwares to Gamma. We can call them directly using the system command prompt, which is also multi-platform since we can use it under Mac, Windows, or Linux. It can also call scripts like R or Python, we use this to make LithuSimGen a really generic software, since we are using ListFluid FP, but another hydrodynamical model called SWAN is tested actually. This genericity makes the game more realistic, since we calculate the real extent of inundation. The main flooding event used in LithuSim is the Xynthia storm, which hit the coast of France in 2010. And territories are in LithuSim are flooded with the real extent calculated by the hydrodynamical model. And when we do the comparison, we can see that results are not very far from reality. As we can see in this picture, so LithuSim was applied to Orléans Island, to the Normandy, to Rochefort, and also to La Camargue, and 2 or 3 other territories are being developed. So Gamma make it also easy to display data via graphical outputs. We can play with aspects of agents. We can depict diagrams with instant updates. We can save all this data to textual files or even to images. This was used in LithuSim to display real indicators, for example, to the leader role that make decisions in real time to punish or to encourage some playing team, depending on their adopted strategies to deal with the flooding events. So I will conclude. So as you see, LithuSimGen is fully dependent on Gamma platform. So any improvement of LithuSim any improvement of Gamma will be reflected on LithuSimGen, especially in some question like portability of Gamma application, because it's not really easy to install Gamma even in tablets. It will be more playful if we have a portable application that we only execute with that double click. In the Opla we have the player role. Gamma needs also some built-in graphical components like I don't know buttons or textual forms, because for now it's not straightforward to build a Gamma interface that accepts events, etc. So this improvement will allow us to develop better simulation that will gives us, of course, better results, especially in this domain of participatory simulations that deal with social and environmental questions. So I will end with the 2 links if people want to know more about LithuSim and how it is implemented. Thank you.
Thank you very much, Ahmed. And we we completed the time, so Etienne doesn't show, but the 2 presentation gets more time, so it's okay. So maybe we can go into discussion. There's a lot of them ongoing on the chat. I've seen. So maybe we can go a little bit on the first and the most discussed question about why to go for tangible rather than a fully interactive touchscreen setup. And this question can be reversed. So for Synerta, it is tangible, and for LithuSim, it is only a touchscreen. So maybe you have both ideas, and you may have insights for us on this.
Yeah, I saw the communication, which is really enjoyable to see that people have some interesting questions. Let's not forget about where I can actually this demand is coming from. So it comes from customers who are looking at their business process. Yes, you can involve the touch screens. You again pick up the solution, like I already noticed, it will serve one person. Solely one person who is to only concentrating on iPad or any other digital solution. So the idea is to involve all people together around, have a simplistic, this is also a keyword, the simplistic and interactive tool to talk about very difficult things which they think that only they understand, because when you talk to the customer, they are professionals. They've been in their business for years and years, and you would like to let them talk. So the way to open up is really to give something which is visually appealing, which is enjoyable to interact, and at the same time you bring some technology in place which gives some analytics, which gives some simulations. That's the major answer I have.
Yeah, I also can add something to it. We're using Lego already in our company quite some time for simulations, and also explaining. We also have sessions with children, for instance. So we were already familiar with Lego as a tool, and but we always looked in a way to combine it with simulation or interactiveness. And so then we saw this solution with the tangible table. It really fitted our own ideas how to do that. So, but that doesn't mean that there are not other ways, and you can use touch screens as well. I mean, this is also just what happened in our organization or historically. So. So yeah, there are more ways to do things in general. But
the good thing, it's working, and you really is surprised to see adult people around the Lego table talking about their business literally for an hour or so, and eventually ending up discussing the business problems. And the only thing you hear, can I try more? Can I do this? What will happen if I do this?
Yeah, you get so many questions.
It's amazing how much people are talking. Can you imagine this with iPad? To some extent, but probably just staring at the screen. But you can wear all kinds of technologies. When iPad comes in place at some point, you can use it.
Yep.
But this is a really conversation breaker. This is a really interactive tool.
Yeah, maybe there's some feedback from LithoSim, because as I know and as I can tell, there's iPad for decision on each actors, but then they move toward a central table where they can see the impact of the actions they made separately. Am I correct, Ahmed?
Yes, exactly.
Yeah.
And have you already think of using some tangible things in this central table, or is it only to display the outcome of each actions?
No, actually, it is just displaying the outcome of the submersion event. But there was some thought about using pen, visual pen, to make actions directly in the display. But actually, it is not implemented yet.
I think we will have a presentation from a German group today about a touchable central screen where several people can interact with the simulation all together. So maybe I can go into other questions. So there's question from the audience first, so I can go for this one. So we addressed the first one, and the other one was more for Irina and the group, how to deal with different spatial scales when you go for a tangible interface like this, because it can be quite a constraint if you want to enlarge the scope, the spatial scope of what you want to represent, or things like this.
Yeah, sure.
Have you thought about this issue?
Oh yes, a lot.
Oh yeah, it's interesting. It's a constraint, but sometimes the constraints help you as well. So in our setting, we also need if we have a really complex simulation, the customer will also not understand it. So the restrictions help us as well to make to really focus on the actual problem. So it kind of helps us in a way as well. But sometimes it feels limiting. Sometimes it's a struggle. But
I saw also the question about the tags and how many agents you can actually cover on the table. Yes, there is limitation. We are currently using white and black as two colors, which are working perfectly at this setting. And you can imagine that with a Lego brick, there is some restriction on dimension. So you end up with a restricted number of agents. For now, we are perfectly fitting, but there are possibilities to extend and make it more discrete on going to the final level. At the end of the day, you can also extend the table if it's needed. So there are possibilities, and we're overcoming these obstacles. And it reflects also on Gamma as well, because Gamma has, of course, to cover a lot of agents if they're on the table. And there is also the way how you handle this technology. I mean,
I think there's a new question that pop up about augmented or virtual reality, but at the end, I think those kind of research will always have a tension between putting more technologies and trying at some point to make it disappear for people to discuss among themselves and to participate and to engage into discussions about the issues and so on. So there's always a tension between putting more technologies and making it disappear for people to enjoy discussing and so on.
Yeah.
Just like I say, it's very difficult to make. It's very easy to make it complex. It's very difficult to keep it on a simple, understandable level. But when the time comes, you can involve the augmented reality. Yes, you can look on the table through the glasses. You can get information by scanning some object. You can think of many things. Do you need it? That's a big question. Yeah.
Okay, so we have still some time. So I have another question, and maybe you can ask new question in the chat. So you were talking about quite quickly about the Ben architecture on the last part of your presentation about Synerta, and I was wondering how you can make those feature of the simulation tangible. I mean, Ben is only about people thinking, agent thinking, and way to make decision, and how you can have people tweaking those feature and variables using tangible interface.
Can you a little bit more speculate on your question?
Yeah, I mean, when you go into a tangible thing, you can move things. So this is spatial. This is very physical. You move the things. But here, when we are talking about Ben, we are talking about decision. So this is not physical. This is not spatial.
No,
so
and that's where that's what Gamma is helping. You can think of, for example, differentiating something with the colors, which project is projected on the table. Like I showed with one example, there was trucks, one color, external logic, one color, for example, another logic. You can also, it is applicable also towards, for example, people, this behavior-driven architecture, which I showed at the end, like an airport. What you saw in the background, it was the way how people were feeling. So the green background was a joyful state. Everybody is entering being joyful. They make a decision, following the decision, they pick up the target, have a target, they make a plan, they make an action, they move. How they feel, you can really differentiate with the colors. You can see people turning from green, for example, to other colors, or the area turning more red, talking about attention, for example, in the queues. That's one example to show how you can make the people feel on the table. And the rest, you can also try to be smart, and you have to be smart the way how you present information with Gamma on the simulation screen. Not to overload with the statistics, how things are changing, to give a feeling something is happening. So it's all about presentation.
Yeah, and I also would like to add, we learn a lot each time we have a new simulation with a new customer. We learn as well how to do that better. So it's for us as well a process. And yeah, so
True. And we're addressing, we are making small step at a time. First of all, it was just a prototype addressing some, for example, mathematical problem to find some shortest distances. Then there was transport logistics, energy sector. Now we have a human behavior, and we still have plans to enlarge this portfolio, and we always get the feedback from customers. So it's still on work to be continued.
Okay, thank you very much. So we have still 2 minutes left to discuss, and I enjoyed a lot the fact that both of you, I mean the presentation within your presentation, you add some feedbacks and even question for the developers. So maybe we'll have some room or some time to discuss about those questions you have for the developers. And maybe there's one you have from Sinerta, where you can find beginning of an answer in LithoSim, which is the how to have Gamma exchange information with other device or in IoT setup or things like that. And I think in LithoSim they have such a things with Gamma. It changes file with other expert model to compute the flood and so on. So there's a lot of exchange. So maybe there's I don't know, ways to find in order for modelers to exchange their solution. Maybe if you have any insight about this, Ahmed, please. And if there's only 1 minute left, but if you have any question for the developers, please ask it on the Slack chat, and you will have some answers, and you can have a discussion about them.
Yeah. By the way, thank you for the great Google group support, because it's a pleasure to get the response and the tips. It's really cool help we have there. Yes.
Yeah, thanks for all the question and all the answers. As Alexis said, they are quite quick. I was pretty surprised to know that 2/3 or 3/4 of the question have been answered in the day when they have been asked. Anyway, so it is 11, so we will switch to the second participatory and modeling session, and I will be the first presenter actually. So
yes.
They were you raised your hand, Alexis, no?
Yes, I was about to complain in the Slack. No, it's just actually I would like to thank Irina for summing up the the problems she found in Gamma, and one of them, the documentation. It is obviously something we need everyone to work on. So basically, when you find dead links, we need to know them, because you can imagine that I don't browse the documentation every day, and neither do any of us. So we really need to, at some point, to have a feedback on this. Even a negative feedback, it's okay. but otherwise, it's impossible for us to know that some links are broken, especially because most of the documentation nowadays is produced automatically. So it's completely automated, and maybe there is a program somewhere just creating every day broken links. Okay, so it is probably something we can fix very easily if it is the case. So please, I know it's a little bit of work to compile all the problems, issues, etc., but for us it's absolutely mandatory to have a feedback on this. So thank you very much in advance.
Yep. So we will start the participatory and modeling simulation 2. We have 3 presentations. The first one is Kevin. So you have 20 minutes to present your works.
Okay, 20 minutes, it's a lot. I thought I was asking for 10 minutes, but anyway. Okay. Let me try to, okay. Give me a few seconds, I'll share my screen. Yep, this one. Can you see the presentation there? Can you see it?
Yes.
Okay, perfect. So I can start. So I will present you an ongoing work. So we do not have yet some results to show. So it will appear a little bit preliminary compared to the two previous presentations. So this is about Brave APM. This is an agent-based integrated approach to study fishery management from the ground. So this is a research made with colleagues in Brazil from the University of Rio de Janeiro, but also the Center for Sustainable Gold in Brazil, IRD, and also CIRAD. So Bones project is a Belmont Forum project. That means that there's several international partners from United States, Norway, and also Brazil and France, of course. It is a project that supports biodiversity in Amazonian floodplain in the context, the wide context of climate change. And I will present the works of the work package 3, which is centered of, sorry, I cannot see the right part of my presentation. So let me put this, okay, sorry. So Work Package 3 focus on participatory modeling to integrate the social and actually to get the social aspect of this issue from the ground, to integrate so this social aspect and ecological determinants of biodiversity changes in the floodplain of Kauai. So this particular floodplain you have here on the screen. So this is in North Brasilia, the Amazonian part of the North Brasilia in the Para state. And you have the floodplain displayed in the center of the screen. So some background about artisanal fishery in the low Amazon. So the floodplains, they have seasonal activities following an hydrological cycle. That is, you have high water level during our winter, and during our summer days, the floodplain is rather dry, and you see the lakes disappear, and you have only scattered small lakes all around. In those environments, fish is one major resource for living for people there, for consumption, but also for economic purposes. And a lot of things to notice about Amazonian floodplain. This particular one, I mean, the Várzea de Kauai, so the floodplain around the city of Kauai, is that it is under next agro-extractivist plan. So this is a collective settlement in progress. It's been 15 years now. It means that the state of Brazil tried to make the people there managing the lands and managing the resources by themselves without any ownership. So this is all collective, but it puts some tension with people that comes from other places, and I would go into it a little bit more. So there's a strong interplay there between local activities, meaning that some are doing cattle ranching, some are doing fishing, and there's tension between those activities. And as I mentioned, this is an open area, so every other actors, non-living actors in the floodplain can enter and fish the fish and extract the resources of the floodplain. So it puts tension again on the collective settlement. What we are doing us there, so we try to model and to support community-based fishery management there. And I will present three steps of our research. The first one is a companion modeling approach. And it begins like a little bit less than 10 years from now with the Clim Fabien, which is a role-playing game. You have a playing session displayed at the left of this playing game. It was focused on local choice of livelihood, either you choose to do cattle ranching or fishing, and what was the determinant of the choices. There's a core mass implementation of this game called Varzea Viva. And my work have been to design a new one, more centered on fishing practices. So we go more in depth into fishing practices and avoid those other activity or trying to make them somehow not as detailed as in the first game. So all this are about role-playing game. You are playing with people there. And there's also two different projects about simulation. So the first one is an agent-based simulation to support this role-playing game. I will present some preliminary simulations. And the last one is something that tried to bring this simulation and at least this one, but also Varzea Viva, so both simulation connected to the role-playing game at higher scales, trying to turn them into some kind of kids model when you can describe wider places, a wider range of socio-ecological processes and so on. So first is the role-playing game. So the idea here is to co-design the game with locals, playing with them. So we embrace the co-mode approach for companion modeling. And I only take two catchphrases from co-mode. The first one is modeling more than models. So the process of modeling is as important as the model itself, meaning that doing the model with people is as important as the model, the outcome of the modeling process, and not foreseen, but co-construct. That means that you cannot come as a scientist, say, things are like that, like that, like that. You should try to forget about all you know and go with people to learn with them. This is something we are quite used to in sociology, but not in computer science. Anyway, so this research have been built on former connections and trust built with locals community in Santarém, and in particular Zedvinch, which is a collective of fishermen there. So as I said, the co-design is here to challenge the scientific point of view and frame issues with the locals and maybe explore solutions using simulation. So this role-playing game called Pesca Viva, the goal of the game, the goals of the game are to support and enhance collective thinking about the issues they can face during the activities of fishing, but also to challenge and calibrate the scientific issues with local actors, meaning that we build the challenges, what we have to simulate, and we want to calibrate those simulations with local actors. We are in the middle of prototyping this game. So you can see a few board games on the right side of the screen. And we focus on spatial aspect of the floodplain. And you can see there's the Rio Grande at the north of the board, but there's also lakes, as I said, there's channel, and there's also this hydrological cycles. So at the top, you can see the floodplain is all water, and then you have some thing in the middle where you have lakes connected, and then the lakes are scattered, they are no more connected, and then again and again. So this cycle is repeated. So we want to introduce this cycle within the game, within several board games actually. And we had some simplistic fish dynamics that like you have degraded renewal of the fish or normal renewal, etc. And this simple fishing practice, it's only consists in putting your boats in some lakes to have more or less fish to fish. There's a big wrong part in this. So we went into the tension between improving this prototype or going playing it with people that allow us to improve with locals, but the third points stand there for the social distancing rules, and in particular when you are trying to work with Brazilian in Brazil, it can get tricky in 2020, also in 2021. Anyway, we nonetheless managed to have some workshops. So we played the fish band games with them in order to introduce our perspective. So they have been convinced playing this game, but they also already start to say this is not something relevant for us, etc., etc. And we're also starting to play our own version among us, so only scientists in a remote way. So it was only using Google Slides and thing and putting both there and there. And from our first try among us, there were a strong need for a calibration tool using simulation. So how many players we need to have some outcome of interest. The one we want was fish scarcity. How long should be the game for this to happen, etc., etc. So now the hybrid agent-based simulation. So this one is trying to put this role-playing game into Gamma, into simulation. And there we have the diagram of activities and actors that we want to represent. I will not go into too much detail because I think I will run out of time anyway. So we put fish in the center. In the top part, you have all the actors of the fisheries in there. So you have fishermen at the left, but you have also people that buy fish, and I will sell them to big industrial boats, and there's plenty of things going on there. And at the bottom of the diagrams, there's people living on the lands and put the codes there, etc., etc., and have impact on the land use and land cover that will have impact on how fish will grow, or etc., etc. So this kind of complex interaction between all the activities, and we try to implement them into a Gamma model, a Gamma simulation. So basically, you can find here the 4 lakes with connection and so on. So we have a network for the connection. So fish and boats can go from one lake to another lake. And basically, the process overview of this simulation is quite simple. So users, they choose a spot where to go fishing. Depending on the number of boats, you will have a certain amount of fish fished there. And then there's a regrow of the stock of fish. And the idea of this simulation was really to calibrate the role-playing game. As you can see on the screen on the right, so this is after 7 cycles of play, and you have the plots on the top right of Gamma. There is the stock of fish for the 4 lakes. So we can see that there's a depletion for, of course, but not as many as we wish. So the idea here is really to calibrate this so it will happen as soon as possible, because when you are doing those kind of role-playing game, time you spend playing is really something important, because if it took 2 hours to go into the state where people has to discuss about why there's no more fish and how they can discuss about them in order to try to overcome this issue, it's too long. 2 hours is too long. So we try to calibrate. And also the idea behind this simulation is also to be able to integrate new feature without having to build new materials to play and so on and so forth. So it's kind of a virtual lab for role-playing games. So we can integrate new feature, do the calibration, and have fish depletion in time. Anyway, I will go to the last part. So the last part is Brave APM is something built on top of this simulation, and that try. So here is just a wish, I think, at that by that time. We try to enlarge a little bit the scope of the simulation and try to be more realistic first regarding environmental aspects. So hydrological cycle, we want to be able not only to simulate 3 stages for 1 year, but every stage every week or every day or every month. We want also to have land cover dynamics, so land use and land change, and we want to have also realistic fish stock growth depending on fish habitat and many other things. And also for the social dynamics, we want to scale up a little bit at for the overall footprint, which is wider than 3,800 kilometers square. So it's quite a challenge to exploit, for example, raster data in Gamma of that range. And we want also to go deeper into the interplays of activities within the floodplains. Anyway, so this simulation, this wider goal simulation, the idea is to calibrate livelihood choices on land cover changes. So at the right, I displayed 3 different land use and land cover images for 3 different years, beginning in the 90s and nowadays. So we have some kind of point on time like this, and we want to calibrate the choice of livelihood of people in order to reproduce those land cover changes. And we also want to provide a stronger link between a kind of toolbox when you can pick some processes like hydrological processes or choice of livelihood to build some or the RPG you want, the best you want. So those kind of things got into a modular aspect of building models in Gamma, and it relates to a question we got during the transport and mobility session about how to build the best modular model in Gamma. And maybe we can have a discussion. So this is more a question about that I raise here. Just to conclude, so we have Pesca Viva, which is a role-playing game. And we are looking for playing it with people in Brazil, but it's still a challenge for now. We are starting to develop a simulated version of this role-playing game called Pesca Viva in Gamma to facilitate, so it is already usable to facilitate the game itself when you play it, for example, supporting the growth of fish, etc., etc. But we want to do more, of course, in order, for example, to calibrate the role-playing game using simulation. And also we have a Brave APM that goes on top of this. And it will be it for me. I hope 20 minutes, perfect. So there's acknowledgement of for the Biodiversity and Belmont Forum that support this research. And thank you very much for your attention.
Thank you. You have 1 minute left. So if you want to add something.
It will be time for discussion after. I think it will be better to have more room for discussions.
So if you have some question, don't hesitate to ask in the channel. So I will switch to the next presentation. Laurie, you have 20 minutes too.
Yes. Can you hear me?
Yep.
Okay, I share my presentation. I think I'm not. Is it full screen?
Yes, it's okay. Thank you.
Okay, so I start. So hello everyone. My name is Laurie Dunn. I'm a 3rd year PhD student at the INRAE agroecology unity in Dijon. And I supervised by Nicolas Chemidelin, Christophe Lang, and Nicolas Mariot. And today I want to present you my subject about spatially explicit modeling of soil microbial communities dynamics at the landscape scale. So it's a bit different from what we already seen. So first, we will talk about soil microorganisms. And by saying this, here we will consider bacteria, archaea, and fungi. Those microorganisms are really abundant and diverse. In 1 gram of soil, you can find up to 1 billion of microorganisms, living organisms, and up to 1 million of different species. And this abundance and diversity can permit to have a diversity and the stability of ecosystem services, such as water and nutrient cycling and quality, and plant growth and health, regulate the climate, also the texture. And so we can imagine a sustainable use of soils. So here, soil microorganisms are good bioindicators of soil quality. They were already studied with the biogeographic studies at different scales, the world, national, territory, landscape, and plot scales. Here you've got the example of the distribution in France. So there is for all these scales, there is a special heterogeneous patchy distribution of both abundance and diversity of those microorganisms. When I said patchy, it's because here, for example, with this map of France, you've got some spots where you found a brown, dark brown color. It's where the abundance of microorganisms, the microorganisms are the most abundant. And on the contrary, there are some spots where it's kind of blue-green, and there is a lower abundance of microorganisms here in terms of DNA. And this spatial heterogeneous distribution is also available at the landscape scale. And in this study, we will focus on the landscape scale because there is a mosaic of agricultural practices, and farmers will have several plots at this landscape scale, not necessarily next to each other. So here the landscape is a decision-making scale. About microbial ecological studies at the landscape scale, there are very few temporal studies. And these temporal studies can permit to identify the effect of human activities, and here the farming practices, on soil quality. So the question was how to predict soil microorganisms dynamics over time in an agricultural context at the landscape scale. We got several models. So the most used actually are the deterministic models where the simulation results will always be the same. So it's for linear models, for example. And you can add also some hazards. So introduce some hazards in your model using the stochastic models. Here, we were thinking about a model that can have both deterministic and stochasticity. So we use a coupling approach based on a multi-agent based system. And also we use this approach because we want to create a decision support instrument. And so we also use a participatory approach. So first, the goal was to predict soil microbial dynamics over time depending on farming management. And well, here I will only focus on the biomass, so the abundance of soil microorganisms at the landscape scale. So how we made it, well, the work is not finished yet, but we used a multi-agent system with a landscape scale as our environment, where you've got several agents. The farmer's agents, which can own plots, where you can find microcells on which there will be some microorganisms who will live and have a dynamics. And also the environment is submitted to the interaction between plants and the climate. So here the rainfall. So farmers can do some practices, agricultural practices on their plots, and this will have an impact on the microcells, so on our microorganisms. And also the interaction between plants and the climate can have an impact on the microorganisms. We use the coupling approach with experimental data, ecological concepts, and also mathematical models, and also the participatory approach, where I will have some details on it. So about the architecture, we use several layers. So we consider the farms owned by the farmers. And those farmers can do activities like tillage, pesticides, sowing, harvest, use some fertilizers on their plots. And here you've got the last layer, which is the more precise one, which I call the microcells, because it contains all the information about the microorganisms. And here we will focus on the abundance of those microorganisms. You've got also the climate aspect, and both climate and farming management will have will drive the behavior of the microorganisms. So here in this case, we use decision trees, regression and decision trees, in order to pick an impact value in a precise distribution of the values, which will have an impact on the microorganisms. And here, so to do so, we use several shapefiles with database. So it's on a real landscape called Fanay. It's next to Dijon. It's a 13-kilometer square landscape where you can find both forests and agricultural plots. And on this landscape, we sampled the soils in 266 points. In 2011, 2016, sorry, and 2019. So 3 sampling campaigns. With this, well, what I didn't say also is that the agricultural practices are known since 2004 in details. So I know we know when and well, the different inputs of the farmers when they do activities, and how many, for example, how many fertilizers, how many pesticides they use, if they use if they plowing the soil or not, etc. So in order to understand the impact of each agricultural practices, we use the recursive decisional trees like this one. And for the growth, we got no information about the microbial growth parameters. So in order to have an idea in how we can make it, we use an exploration based on our database. So about the calibration of the model, we want to predict soil microbial biomass dynamics. So first, we've got an initial value from the first campaign in 2011. And in the bibliography, we find out that the molecular microbial biomass follow a logistic growth. So here, the main goal was to find the microbial growth parameters in no impact conditions. So with the K, the carrying capacity, and A, the growth rate. And when we have an impact, here, for example, the tillage, the plowing, we've got to identify the impact of the practice. So it can be higher or lower than our initial values, and also the time effect of each agricultural practices. I just said that for the growth parameters, we used a logistic growth. So here we have to resolve the two unknown parameters. For this, we use a genetic batch experiment with 100,000 iterations, and we discriminate based on the root mean square error. So we got 15% of our iterations that were, well, with a root mean square error quite good. And here is the more precise results, where we found that in order to, well, the best growth parameters were when the carrying capacity and the growth rate was both low. We select 8 paired parameters, and we identify the time impact launching several simulations with various parameters. So the growth, the 8 pairs of parameters, and the different time impact, 7 days, but 7 days. The work is in progress. So now I will present you another aspect of this work, so about the participatory model. We've got this soil agent-based model, and we want it to have a participatory model. So in order to do this, we created several models. So here is the interface of the players. It's really similar to the lithosim. The way we create it, it's really similar to the lithosim. So we've got several players on the same, workshops, and each player had a computer, and they had to complete farming practices for 1 year. So they were it's a role playing game. They were farmers. So here, for example, they had the tillage, and then they were sowing some rapeseed and adding some pesticides. Each players had, it's on the real plots. So each players had 4 plots at the same time, and they had to complete for 1 year all the different practices. And then we had all this information were were compiled in a computer server, and we were all around the table where we had the different results for the year. So each players can see what the others have had in terms of practices, and how the soil microbial biomass evolved over time. So the serious game here about the scenario and the goals. For the individual part, the players, so the farmers, have to try to maintain or improve their soil microbial biomass on their croplands, and they had to complete agricultural practices for 1 year. And in the collective aspect, they had to share ideas and try to solve a collective problem together. So here is the plan of the workshop. So there were several players. The player one in reality was, well, each player were in reality played by 2 or 3 people at the same time. And here it's the individual part. Then we have the collective part with the server and the display where everyone can see on the table the results. Here is the pictures of this is the first workshops made with farmers. So the individual aspect and the collective aspect. And we also have a game progress. It means that I first introduced the serious game, and then the interface were owned by each players. And then the game starts with several rounds. One round is equal to 1 year. At the end of the year, so the end of the round, there was a debriefing. And the third year, we introduced invasive plant species, and they had to manage it individually and collectively. So it was also the goal to see if they will be all together in order to manage this or alone. And then at the end of the game, we had a debriefing. So we had the calibration. So the idea was to share with experts with the participatory modeling. I talk about farmers because the role player is a farm. But in reality, we made it with farmers, advisors, research community, and also students. So the goals was to test and evaluate the interface, the model, the soil microbiome model, share experience, and imagine new farming management during this workshop. So we had the usability interface. We also have new farming management, so we can explore the model with this, and check the result viability, and improve the model. So there were various, here it's the end of my model. Well, we've got various aspects in order to explore the model. So here we can explore the model only on a cluster with the sensitivity analysis in order to identify the parameters, the redundancy at parameters with Monte Carlo iteration, the confrontation with experts, which are already been done during the participatory workshops, sorry. We also had the step about the focus on results, so the exploration based on intelligent algorithms, and check that the model can be operational. So that's another part, and we had to test it on external data. About the enhancement of the models, we can, well, the model can be flexible. It means that we can add new functions, like for example, in our case, there were no, pretty few adding of organic matter and no mulching. So we can add some new functions. And also I talk about the operationality of the model. So for example, here we worked on a specified landscape with a specified soil and climate conditions. So we can test the model in other soil and climate conditions, other practices, and with initial value of biomass, so with a monitoring over time. So for this, for the both, we had to use external database. In conclusion, we had a spatially explicit model on soil microbial biomass, and we used an original methodology based on a multi-agent system. And this model was created based on experimental data and ecological and mathematical concepts. in terms of perspective, we have to finish the exploration and the sensitivity analysis and transpose the methodology for soil bacterial diversity and community composition. Thank you.
On the time perfectly. Thank you for your presentation. So if you have some question, don't hesitate to ask your question in the chat. And now we will switch to the last presentation of this session. Youssef, if you are here.
Yes. Good morning.
Okay.
Do you hear me?
Yep.
Okay. Okay, just time to share my screen. Okay. Okay. Can you see my screen?
No.
Not yet?
Not yet.
Okay, desktop, more point. Oh, sorry.
Okay.
Now, can you see my screen now?
Yes, you have 10 minutes.
Okay, thank you. Okay. Good morning, everybody. I'm Youssef Sklab, the studies engineer at UNESCO IRD. And today I'm going to present you part of our work entitled Gamma, Unity, and Interactive End User Interface for Participatory Modeling with Gamma, which consists of developing a new participatory modeling and simulation feature for Gamma, a work that I'm doing with Nicolas Mariou. The typical purposes for this feature will be then, for instance, for building serious games as a support for decision-making processes. In such situations, it is necessary to simplify interactions and integrate relevant feedbacks among complex systems into the model. So the stakeholders can make direct changes within the simulation process, as well as see the results of their changes almost instantly. This work is still in progress, and for my part, I do not have a specific implemented model, but I have some small running examples that I can show you later. But the question is, for why you use Unity? Simply because Unity is a cross-platform game engine, and a scene in Unity can be run on several devices with different platforms or operating systems, like Windows, macOS, Linux, or Android, or iOS, etc. In a concrete way, our work consists in developing a Gamma plugin and Unity client. The Gamma plugin offers or will offer to the agents on Gamma a new skill that we call Unity, offering them capabilities to interact with the stakeholders and get their feedbacks through remote devices where the Unity client is running. So all we have is to build the Unity client for the targeted device. Till now, there are two possibilities of using the Unity client with Gamma. The first one is with what we call a generic scene, and the second one is what we call a model-specific scene or a customized scene. The generic scene is intended to be used for example, visualization purposes, visualization of simulations on Unity. It is not finished yet, but it already supports several functionalities and can be used for to visualize or for visualization of several models running on Gamma. The model-specific scene is intended to be used for models that require specific functionalities. It is the case here, for example, for some serious games having complex user interfaces. Here modelers should have coding skills in Unity, which is not required in the first case with a generic scene. Okay, so how it works, what we till now, we have a Unity client which relies on two existing features in Gamma. The first one is network skills, that we use network skills to manage network connection and message exchanges between Gamma and Unity. And the remote plugin, which provides reliable mechanism to publish data values to distant clients when changes occur during simulation. Recently, we add the support of the gaming skills. The communication between Gamma and Unity is made following the MQTT protocol using an MQTT broker. More precisely, exchanging messages between Gamma and Unity is built following a publish-subscribe model that involves Gamma agents on one hand and Unity game object on other hand. A game object on Unity can be seen as an agent on Gamma. It's having the attributes, actions to perform, reflex, aspects, code to run at the beginning or at every cycle, and many other similar things. So the communication between Gamma and Gamma agent and Gamma Unity game object is managed by topics. For example, to send a message from Gamma to Unity, the Gamma agent has to publish the message, that message on a topic T, for example, to the MQTT broker. And to receive that message by Unity game objects, it has to subscribe to the MQTT broker under the same topic T here, for example. So the MQTT broker will deliver all the messages that it receives on that topic to all the game object that has subscribed to it with the topic T. This way, we can have several topics with several game agents and Gamma agents and communicating with other game objects on Unity, on the Unity side. In more details, till now, the kind of messages that we have, or that we can send from Gamma to Unity or from Unity to Gamma, we can classify them into two categories: unidirectional messages or asynchronous messages, and bidirectional messages or asynchronous messages. In the first category, we can send here from bidirectional because we can send the message only from Gamma to Unity, for example, in this first category. The first kind of messages is that one we can use to send the Gamma agent from Unity, from Gamma to Unity. So we will create an equivalent agent in Unity having the same attributes, the same shape, color, etc. Not all the attributes, but we can send lot of attributes from Gamma to Unity. A second kind of message is to set a value for example, a given attribute in Unity, or to set a value for a Unity property, for example, to configure or to set the environment in Unity scene. We can also ask from Gamma to Unity to run a specific action on Unity. We can perform, for example, change a location for an agent or a Gamma a game object on Unity, or just to ask to move an object or a game object in Unity in a smooth way. We can here, for example, precise the speed. We can also destroy a game object. So in Gamma, it will be kill an agent. The second category, which is asynchronous messages or bidirectional messages, we have two subcategories. The first one, we let the modeler to set the topic and the content of the message. So the modeler can send the message from Gamma to Unity and to Unity from Unity to Gamma at following his needs. He can set the topic that he needs and the content of the message that he needs. The second subcategory is bidirectional messages, but Gamma can ask and Unity can reply. So we can ask for a certain value of an attribute and Unity will reply with that value. And we can, for example, from Gamma ask or to subscribe to a notification. So Gamma will ask Unity to be informed when certain condition is verified or is true on Unity. Okay. The use cases of the Unity client can be, for example, for this kind of purposes: visualization, user interaction, event notification, user command, or user input. We will show you some examples quickly. For example, for the first use case, we can here we can visualize the simulation of the model that exists in Gamma library, which is the building elevation model. In the second case, it is a case of distance sync control or notification events. Here, it is a kind of game, actually, which consists of a ball, which is controlled by an agent on Gamma, and Gamma will, an agent on Gamma that will move the ball in a random way in different directions, and when the ball meets a cube here, the cube will disappear. The cubes here are not managed by Gamma. So another example of notification here can be is.
You have to conclude.
Sorry?
You have to conclude your presentation.
Okay, thank you. Sorry. Okay, sorry. Go on. Just here, and another example is when to use, for example, user interaction. We use a part of the interface developed for a LithoSim project, which is developed, I think, by Nicolas Mario and Benoît Godou, which we can use also for user command. Or here, another example for user input, where the user can send different values of different attributes to Gamma. That's it. So it's the end of my presentation. Thank you for your attention. Sorry for the delay.
No problem. Thank you everyone for your presentation. It was very interesting. And now we will switch to the discussion. I have some question. Okay, I will start with a question for Laurie. How was built the decision tree from Patrick Taillandier?
Yes, about the decision trees, we use, well, we have the 3 different steps in my PhD. So the first one was to describe and understand the special patterns of soil microbes, and also try to understand how they evolve in function of the farming practices. So for this, we use the RStudio software. So those analyses, the decision trees, were computed thanks to the function rpart. So it's recursive and partitioning trees. And we've got, so we created for each type of practices, I mean, tillage, fertilizers, pesticides, and crop rotation, we create one decision tree with when we've got the several distribution of biomass in this case, and we compute this distribution into Gamma, the language Gamel, and we ask each time whether those practices are made by the farmers. In the model, we ask the farmers to pick a value in those distribution in each leaf, well, the leaf of the trees corresponding to the action. So that's how we made it.
Okay, thank you for that. I have a question. There is a lot of question actually, but I have a question for Kevin about Brave ABM. Do you have any hydrological model in mind? And yes.
Yeah.
What is the complete
this was
approach?
also a question addressed by Deborah in the chat. And in fact, we saw a lot of models using or turning around flood and floodings and hydrological model that can be of any use. Actually, we did something when I were in Vietnam with Benoit and an internship to connect ECRAS, which is a specific hydrological tool to build models, hydrological models, to couple this tool with Gamma, but it's kind of technique intensive solution. So I am working on solutions that can be built quite easily within Gamma. And you already can build things within Gamma using dispersion within a grid. But for now, they are not scalable at all. And here, in my case, we were dealing with huge places like more than 3,800 kilometers square. So we are looking forward for new features to be included in 1.8.2 to deal with big raster file. And there we will be able to use Gamma capabilities in terms of diffusion or other kind of processes to model quite easily hydrological, dynamic, flood, everything.
Okay.
So just keep up to date with 1.8.2, and I will drop some models in the model library in order to use those new features.
Okay, thank you. Thank you for your answer. I have a question for you, Steph. I have two questions. The first one is your skill can be used with the headless Gamma in order to have Unity has the interface of Gamma, for example. And also the second one is the plugin is already available or not? Youssef, are you here?
Do you hear me? Sorry.
Yes, yes.
Yes, for the second question, if the plugin is already available, the plugin is we are still developing the plugin. So I can say it is available for some use cases, but to use it for complex scenarios, it is not finished, and it will be a bit hard to use it. But till now, for simple use cases, it is we can use it, and I can say it is available for that. We can install it on Gamma and start using it. For the second question, it's about
Headless Gamma.
Headless Gamma. If we can use this plugin with Headless Gamma, I don't think. Yes, we can use it because I think we can use it. I didn't. I think that we can use it because we can use Gamma without user interface, for example, and communicate through the network with the Unity client. So yes, we can use it with headless mode.
I have another question about the MQTT broker. The MQTT broker is in the skill, or is you can use it for another thing?
In the skill now, the MQTT broker, we install it separately. We run it separately from Gamma. We use the network skills in Gamma to use the MQTT broker. So sorry, which was exactly the question?
My question is, it's possible to use the MQTT connection for
other purposes, for example?
Purposes,
yeah, it is possible to use it. There is a lot of models that use MQTT broker for other purposes, yes.
Okay, thank you. I have a question for Kevin and Laurie about the boundary territory isn't there and the edge effects. Yeah, the choice of boundary of the territory. Exactly. The question is from Titan Patrick.
I don't know who is starting, so maybe
Yeah.
I start.
Go ahead, Louis.
So about the boundary, yes, it's true that we, for the moment, we only worked on the funny landscape. So it's, as I said, it's a 13 kilometer square landscape on the north of Dijon in France. However, for the moment, we know that this model is available only on the funny parameters, so the soil depth, the climate, also on the conventional agricultural practices, because on this landscape it was only conventional. However, we are trying to explore the model in order to see if the model can also be available on other practices. And also we've got several other databases with measured data, so we can use the model with new inputs and a new shapefile, well, with other territories in France, and see if the results are quite good, quite predicted or not, and so add some new functions or corrections to the model.
Thank you.
And yeah, to answer this question, so it's a very, very good question when it comes to modeling ecological dynamics, because you cannot put boundaries around those kind of processes. So it's always a question, and for us, because we go into some participatory parts where you do not have any simulation, those kind of things can be introduced in quite an easy way, like you have some perturbation, exogenous perturbation that comes and change the things within the role-playing game. But when it comes to simulation, you have to take it more into account for sure. But we have differential response, I think, depending on the processes you target. For example, if you target hydrological processes, you can have some kind of scenarios, for example, to account for those exogenous impacts, like a big flood coming from a dam that break upstream of the Amazon, or even climate change of broader scope scenarios. But when it comes to fish moving, for example, because they are migrating fish species in the Varzea and others that stick to the floodplain, it's a more difficult question, and I do not have any answer. And it's pretty much the same for Laurie, I think, because when you are dealing with population, how it grows and so on, maybe you can cluster those population, but there's boundaries, and I do not have any answer, and we have to rely on expert model, exogenous model, to deal with those kind of boundary condition, I think, not on agent-based rules. But
okay.
Yeah,
Thank you.
My 50 cents.
Thank you for your presentation. This is the end of this session. If you have any more questions, do not hesitate to use the channel. I see there is some question that I will not already answered. I don't know. And that's it. Thank you for your presentation. And this is 1 hour lunch. And have a good lunch.
Yeah, have a good lunch, everyone.
Thank
See
you
you
very
this
much.
afternoon.